Good morning, everyone. My name is Maria Jessica Elinabae, and I'm going to discuss about the chapter 7, which is the cardiovascular system. First is the role of cardiovascular system. So, the cardiovascular system is a complex transport network that consists of the heart, blood, and blood vessels. It acts in a coordinated fashion to maintain blood pressure throughout the circulation. So, ang heart, blood, and blood vessels is sila nag-play sa cardiovascular system, ga-circulate sila para mag-work ang overall na cardiovascular system. So the blood pressure is the driving force for blood flow. When the tissues need more oxygen and energy because of greater metabolic activity, the cardiovascular system responds by increasing its output and pressure to deliver more blood. So, for example, is mag-perform ka mo sa mga vigorous intensity ng mga exercises or activity. So, the more nga gakabad siya to sa kapoy is nagadasig ang pag-pump sa inyong heart. So, the more nga nagapump ang inyong heart is mas ga-pusog ang pressure na sa inyong heart. So, ang pressure is more strong if mas buglay ang mga gina-perform ng mga physical activity or exercises. Next is the anatomy of the heart. So, the key aspects of heart anatomy are the heart pump, the cardiac tissue, the pericardium, the cardiac wall, and the myocardium. Heart pump. The heart is a four-chambered organ that consists of the two atria and two ventricles that work as dual pump to deliver the blood to all body organs and tissues. So, atria and ventricles, so duwa-duwa ni sila, tugubuligay sila, na mag-pump ang heart and to deliver more blood throughout the body and our organs. So, the right heart pump includes the right atrium and right ventricle and drives blood through the pulmonary circulation, whereas the left heart pump consists of the left atrium and the left ventricle and drives blood through the systemic circulation. Next is cardiac tissue. So cardiac muscle tissue is one of the three types of muscle tissue in your body. So the other two types of skeletal muscle tissue and smooth muscle tissue. So the cardiac muscle tissue is only found in your heart's device, where it performs coordinated contractions that allow your heart to pump blood through your circulatory system. So when we say contractions is the mas ginapahugot pagin kag the more nga may contractions is the more nga nagapump ang blood. Next is pericardium. So the pericardium or pericardial sac serves as a protective covering over the heart and anchors the large blood vessels entering and existing the heart. So a pericardium is kumbaga isa siya ka-layer nga nag-protect or naga-cover sa atong heart para mas maprotektahan pagin kag ma-anchor ang large blood vessels entering and existing the heart. So, it is a fluid-filled sac that surrounds the roots of the major blood vessels that extend. So, there's a figure. This is the layers of the cardiac wall, which is the endocardium, myocardium, and epicardium. So, next is the cardiac wall. So, the cardiac wall consists of three layers, which is the endocardium, myocardium, and epicardium. So, amin siya kabilang sa figure 7, which is the layers of cardiac wall. So, the endocardium is the innermost layer of the heart and lines all the chambers of the heart and cardiac valves. The structure of the endocardium contains endothelial cells and tough, elastic, connective tissue under the cells. So, when we say endocardium this is ang pinakasulod na layer sa heart. Amo na yung nag-align sa chambers and heart and cardiac valves. So, siya yung first and inner layer din sa heart. Next is the myocardium. So, the myocardium is the middle and the largest of the cardiac wall layers. So, kung ang endocardium is the innermost layer, what is ang myocardium na naman niya ay sa middle sa or ikaduwa sa largest, middle and the largest of the cardiac wall layers. This layer consists of cardiac muscle, which contracts and generates the pressure needed to inject blood out of the heart. The myocardium layer is in the atria is thin as 2 to 3 millimeters compared with the ventricles, and is largest in the left ventricle, which is 10 to 15 millimeters. So sa atria is mas gamay siya, mas nipis siya compared sa ventricles na ang iyang measure is 10 to 15 millimeters because of the need to pump blood through the entire systemic vascular system. Next is the epicardium. So the epicardium is the outermost layer. So kung ang endocardium is the innermost and the myocardium is the middle layer, the cardiac wall. The epicardium is the outermost layer. Siya yung pinaka-guwa-guwa din na layer sa cardiac wall. The epicardium is the outermost layer of the heart and is synonymous with the visceral pericardium. This layer houses the major coronary, blood vessels, cardiac nerves, and other small vessels. So, sa sininga layer is gina-connect niya ang the major coronary blood vessels, which is and the cardiac nerves and other small vessels. So, there's the connectivity. So, the next is the pulmonary and systemic circulation. So the pulmonary circulation includes the pulmonary arteries that perfuse the lungs for gas exchange and pulmonary veins that return blood to the heart. The systemic circulation is represented by the systemic arteries that supply blood to all other organs and tissues and veins that return blood back to heart. So amo ni sa figure, which is Figure 74, general organization of the cardiovascular system. Next, so the cardiovascular system contains two interconnected circulatory networks, which is the pulmonary circulation and the systemic circulation. So the pulmonary circulation includes the right atrium and the right ventricle, or the right heart pump, and the pulmonary arteries and veins. While the systemic circulation is composed of the left atrium and ventricle, or the left heart pump, so the aorta and all other blood vessels. These include arteries, arterioles, capillaries, venules, and veins. So the responsibility of the systemic circulation is to deliver fresh oxygenated blood to the peripheral organs and tissues. So ang role ni Drea kung goal is may healthy nga blood nga mas ma-deliver din sa peripheral organs and tissues. As the systemic arteries approach organs and tissues, they branch extensively and become smaller vessels known as arterioles. So the extensive branching of the arteries into smaller arterioles causes a large drop in driving pressure that helps to slow down the transport of blood at the tissues. So this is important function helps to regulate the distribution of blood to specific organs and tissues depending on their metabolic needs. The extensive branching of the arteries into smaller arterioles causes a large drop in driving pressure. So nag-help siya para large sa arterioles, ang large drop nga nakatabo dira is kung may large drop sa driving pressure, mas nagugulit siya kung mag-slow down ang transport sa blood sa tissues para hindi pa hulubihan. So the arterioles continue to branch and eventually develop the tiny beds of blood vessels known as capillaries. So, mas nagadevelop pagin siya kag gihimo siya nga capillaries, and which is the smallest and most numerous of all blood vessels in the body. Capillaries are located at the blood cell interface and connect the arterioles to the veins. So they contain a thin layer of porous endothelial cells that allows for the rapid transfer of gases, nutrients, and waste products to all and from the tissues. As the transfer of substance between the blood and tissues takes place, the capillaries are drained by larger vessels called venules. So, larger vessels naman yung pakantuan kung mag-transfer ng substance between the blood and the and it takes the tissues takes place. So, nag-create naman siya sa venules. So, venules begin the process of returning oxygen-poor venous blood from the systemic organs and musculature to the heart. So, venules eventually become larger and merge to form veins. So, kung nag-large pa rin siya nga nag-large, so, mas malaki na iyang itsura kag magwa na rin siya nga isa na rin sa veins. The blood flows through the heart and into the stem circulation is driven in part by a pressure gradient that is established by the left heart pump. For instance, as shown in the figure 7 to 6, which is the average perfusion pressures or the mmHg inside the heart. For instance, as shown in figure 7 to 6 under resting conditions, the average pressure in the left ventricle and aorta is about 120 mmHg, whereas the pressure in the right atrium is much lower. So, mas lower pag hindi siya sa right kaysa sa left. So, it creates a pressure gradient of 118 mmHg. Therefore, because the pressure is much higher in the aorta, blood flow will flow to the aorta of lower pressure or in the right atrium. So this pressure differences drives blood across the systemic circulation. In figure 7 to 7 illustrates the changes of blood pressure, blood flow, velocity, and cross-sectional area of vessels across the systemic circulation. So the small internal diameter of small arteries and arterioles creates a high resistance to blood flow contributing to the sharp decline of BP. Coronary circulation. The coronary circulation system is a special system of blood vessels that supplies the myocardium with blood, and the coronary circulation begins with the right and left main coronary arteries. So, each of these main branches starts as small openings in the aortic trunk or ascending aorta that are situated just above the aortic valve. So, ang isang illustration, which is the major arteries of the coronary circulation. The majority of blood flow through the coronary system occurs during diastole, or when we say diastole it is the relaxing of the heart, and the total amount of the blood flow is most influenced by aortic pressure during diastole. So, with the greater pressure in the diastole, the greater coronary blood flow, and the duration of diastole or the longer duration, the greater coronary blood flow. The cardiac electrical conduction. So, this section focuses on the blood flow of electrical impulses or the action potentials in the heart that triggers the myocardium to contract. Just like with skeletal muscle, so cardiac muscle must be stimulated to contract by nerve impulses. So these impulses are conducted within the heart from cell to cell during a process termed depolarization. So when we say depolarization, nag-occur na din kung heart is in process. So when we say depolarization, it involves the exchange of sodium and potassium across the cell membrane. So specifically, these impulses cause the release of calcium into the myocardial cell, which allows the binding of actin and myosin so muscle contraction can proceed. So without the calcium present, muscle contraction cannot occur. So kung wala ang presence sa calcium is wala man contraction na ma-occur sa ating heart. So it calls the depolarization. This is the figure 7 to 10, which is the cardiac conduction system. So the important structures of the cardiac conduction system are as follows. Number one is sinoatrial node, the AV node or an AV bundle, and the third is right and left ventricle branches. Fourth is Purkinje fiber network. Electrocardiogram. So the electrocardiogram or the ECG is a recording of the flow of electrical activity that occurs in the heart during one heartbeat. So there is a electrical activity kada beats ng atong heart. So the ECG offers clinical professionals information on the function and structure of the heart at rest during activity. So ang electrocardiogram is makita na siya sa commonly sa hospital para makita ang sitwasyon kung healthy pa ang pag-beat sa heart sa isa ka pasyente. Function is determined by the heart's ability to conduct impulses or depolarize in an organized and uniform manner every heartbeat, while the structure is determined by the size and shape of the waveforms of the ECG recording. The ECG is an important diagnostic tool to help determine whether a person is underlying cardiovascular disease. So, amo na siya ang ginagamit para mabalaan kung hanggang kanina kung healthy pa ang sitwasyon sa heart sa isang pasyente. Mabalaan din kung nag-underlie sa cardiovascular disease. So, a normal resting of the ECG is shown in the figure 7 to 11. So, each waveform of the ECG is related to specific electrical event during one heartbeat. So, next is the cardiac cycle. The sequence of electrical and mechanical events that occur during one heartbeat is known as the cardiac cycle. So, mechanical events refer to the contraction and relaxation of the heart's chambers. So, the relaxation, the phase is called diastole. So, diastole, diastole is ginatungod na is the relaxation phase, and whereas the contraction phase naman niya, the heartbeat is called the systole. So, the diastole and systole differ from each other. So the cardiac cycle can be divided into four distinct phases, which is the phase 1 is ventricular filling, phase 2 isovolumetric contraction, the phase 3 ventricular ejection, and the phase 4 is isovolumetric relaxation. So in phase 1, which is the ventricular filling, during this phase, the heart is in the diastole. So during the first 2/3 of diastole, the right and the left ventricles fill passively with blood. And in phase 2 is the contraction, it is the beginning of systole and commences when the ventricles depolarize. When the ventricles depolarize, they contract and build up pressure. The ventricular contraction proceeds into a very specific direction from the bottom to the top of the heart to ensure that blood moves toward the semilunar valves and can be ejected out of the heart. So sa semilunar valves naman yung pakantuan sa pag-flow ng blood in a ventricular contraction. So the phase 3, which is the ventricular ejection. So ventricular ejection can be subdivided into rapid ejection phase and a reduced ejection phase. Rapid ejection is characterized by number 1, a sharp rise in ventricular pressure, number 2, a steep increase in aortic pressure, and number 3, a reduction in ventricular blood volume as blood flows quickly into the aorta or pulmonary artery for the right ventricle. And the phase 4 is the isovolumetric relaxation. So the onset of the phase 4 marks the end of the ventricular systole and the beginning of ventricular diastole. So it is represented by an abrupt closure of the aortic and pulmonary valves. Since all valves are closed, no blood can enter the ventricles. So as a result, the ventricular myocardium undergoes a period of isovolumetric relaxation that is characterized, and eventually ventricular pressure drops below atrial pressure and the tricuspid mitral valves open once again. So the net effect is beginning of another cardiac cycle with the reopening of the AV valves and ventricular filling, which is in phase 1. So next topic is regulation of stroke volume. So the amount of blood ejected by the heart in one beat is the ventricular stroke volume. In cardiovascular physiology, stroke volume is the volume of blood pumped from the left ventricle per beat. So, the stroke volume is calculated using measurements of ventricle volumes from an echocardiogram and subtract the volume of blood into the ventricle at the end of the beat, or called end-systolic volume from the volume of blood just prior to the beat. So, by measure na sa pag-beat sa ating heart and may calculations. So the stroke volume is regulated by three variables. So number one, the end diastolic volume or the EDV, which is the volume of the blood in the ventricles at the end of diastole. Number two is the total peripheral resistance, which is the frictional resistance or the impedance of to blood flow in the arteries. And number three is the contractility or strength of the ventricular contraction. So there are many additional factors that can influence SB. This include the following: the venous return, plasma volume, ventricular filling time, ventricular chamber size, and the afterload. So the venous return is a primary factor that affects SB. Is the amount of blood that's returned to the heart from the peripheral veins. So, ang ginhalinan niya is sa peripheral veins. Pag ang blood is nag-circulate sa naman siya natawag na venous return. So, when the venous blood returns and enters the ventricles during diastole, it increases EDV and stretches the myocardium before contraction. So, this figure shows the relation among the EDV or the influence of end diastolic volume after load and contractility on stroke volume. So, this is an illustration. So, as the volume of blood is increased in the left ventricle, the amount of blood ejected per heartbeat is also increased to a similar extent according to the middle line. So, ano siya, ang red line. And as afterload and contractility increase or decrease, the SB curve is either shifted up or down for a given EDV. So next, plasma volume. So the plasma volume. Plasma consists mostly of water, electrolytes, and plasma proteins. Dehydration, which lowers plasma volume, has a negative impact on SB. So, may negative ini sa effect sa atong stroke volume if magnubo ang atong plasma volume. The problem with the significant decline in plasma volume is that it lowers venous return and ventricular filling pressure. So, kung malaki ta sa plasma volume is maapektuhan niya ang venous return kag ang ventricular filling pressure. So, in turn, the EDV and the load are reduced, which will lower myocardial stretch and ventricular contractility, producing a lower SB. So, conversely, regular exercise training in hot and humid conditions can actually increase plasma volume. So, ang solution ng nada is, kung gusto mo nga maka-avoid sa amin nga sitwasyon is mag-perform ka sa mga exercises nga mabalhasan kay palaw kag amo ning makabulig para hindi ka malak sa plasma volume. Next is ventricular filling time. So another factor that can influence SB and EDB is the ventricular filling time. So for a normal resting heart rate of 70 beats per minute, one cardiac cycle takes 0.1 second with approximately 0.5 second. An important distinction to understand is that even though there is a less ventricular filling time, high heart rates, SVs will still be higher than resting conditions because number one, venous return is increased through the skeletal muscle pump. So, ang venous return is mataas siya sa pag contribute din siya sa contribute siya sa skeletal muscle pump natin. And number two is the increased force of contraction that occurs through the Frank-Starling mechanism results in more complete emptying of blood. So, makalingaw kita nga malakman kita sa blood. So, ang naka-important ang pag-intindi natin sa ventricular filling during the blood flow. So, number three. Next is ventricular chamber size. So, the size of the left ventricle also influence SB. So, it increased ventricular chamber size can accommodate a greater filling volume and subsequently a greater SB through the Frank-Starling mechanism. One of the benefits of regular endurance exercise training on the cardiovascular performance is ventricular chamber enlargements, which helps to increase cardiac output. So, pag dako siyang ma-contribute sa physical exercises or physical activities para atang nga ventricular chamber is magdako pagit kag kung magdako ni siya is mag-help siyang mag-increase ang atang nga cardiac output. And the last one is the afterload. So the resistance to eject blood of the heart is known as the afterload. So a greater afterload has a negative effect on the SB. That is, increased afterload will decrease SB. So the primary reason for the reduction in the SB is because there is a less complete emptying of blood resulting in a higher ESB. So therefore, although ADB or the endosolic volume may not be affected, a greater afterload limits the amount of blood that can be ejected from the left ventricle. So the next topic is about the cardiac terminology. The first one, cardiac output. Cardiac output is an excellent reflection of the rate of the blood flow through the cardiovascular system. So it increases in heart rate adaptation will increase cardiac output, and this is especially important during exercise when blood flow must substantially increase to meet the metabolic demands of the working muscle. In the resting Q or the cardiac output ranges from 5 to 6 liters per minute, and during exercise it can increase to more than 30 liters per minute in endurance trained individuals. So, kung mas nagalawig pa ganun yung pag-perform sa exercise is mas nagataas siya kada minuto yung mga cardiac output. And taking into consideration the normal blood volume of 5 liters in the cardiovascular system, the heart recirculates this volume once every minute at rest and up to the 6 or 7 times that amount per minute during exercise. So, mas may kataas pag siya kataas, the more ka mag-perform sa exercise. The next is the arterial blood pressure. Systolic blood pressure, or the SBP, is the pressure exerted on the systemic arterial walls during the period of ventricular systole, or the contraction. Diastolic blood is the pressure exerted during the period of ventricular diastole, or the relaxation. The mathematical difference between these two pressures is termed the pulse pressure. And SBP and DBP are reported together as ratio when measured when systolic pressure is numerator and diastolic pressure. So the average BP in the cardiovascular system can be estimated by the mean arterial pressure or the MAP. So the MAP is difficult to directly measure in the vascular system. So hindi siya dali-dali yung measure. Kag may ara siya nga formula. However, data from SBP and DBP can be used to mathematically estimate MAP to the following equation. So ang data nga sa SBP kag DBP is dako na siyang mabulit nga para ma-solve ang kag makuha ang MAP. Amo na siyang equation. So MAP or the millimeter Hg is equals to SBP minus DBP times 0.33 plus DBP. So in this manner, MAP is equal to 1/3 of the PP plus the DBP. So ano siyang magawa na solution, which is the 1/3. And this is due to the difference of the time the heart is in systole and diastole. So nagdepende man siya sa time na kung saan may matabo nga systole kang diastole sa ating heart. So rate pressure product is the product of HR and SBP. So naman niyang may equation man siya, which is the RBP is equals to HR times the SBP. So it is standard practice not to report units when calculating the RBP as a non-invasive measurement. It is a good index of myocardial oxygen demand at rest during activity. So next is the ejection fraction. So a normal ejection fraction ranges from approximately 55% to 70% at rest and can increase with exercise or up to 80%. So an abnormal or pathological EF or ejection fraction is less than 50%. So an ejection fraction at this level is an important clinical measure to determine the severity of myocardial disease. The next topic is about the hemodynamics. So the hemodynamics is a study of factors that contribute to the flow of blood through the cardiovascular system. It is tightly regulated by alterations in pressure, flow, and vascular resistance. So it recalled that blood flow through the systemic circulation is the result of pressure difference established by the left heart pump. So the pressure is the highest in the aorta and the lowest in the right atrium. So ang pressure sa hemodynamics is mas dako siya sa aorta compared to the right atrium. And it creates a high pressure gradient that drives blood through the systemic circulation. So consequently, changes in BP can have a profound effect on the amount of blood that circulates through the vascular system. So in contrast, if heart rate increases or if the heart contracts more forcefully, so the delivery of blood will also increase. So the more na nag-contract ang atong heart is mas taas ang blood na gina-deliver throughout our tissues or organs. So finally, changes in the resistance provided by the circulation can also affect the flow of the blood. So, relation among pressure, cardiac output, and vascular resistance. So, MAP is the average blood pressure within the cardiovascular system. So, it was calculated as DBP plus 0.33. And another way to calculate MAP is to multiply cardiac output by TPR. So this relation is shown in the following equation. So MAP is equals to cardiac output times the TPR. An increase in cardiac output or TPR will increase blood pressure, whereas the decrease in cardiac output is resistance will lower BP. So the rearranging and the above equation and solving for cardiac output demonstrates how changes in pressure and resistance affect blood flow. So, ang sa sininga equation is may go ka makita mo ang pressure at resistance nga nag-affect sa atong nga pag-flow sa atong blood. So, it should become evident that the rate of blood flow through the circulation is proportional to the pressure, but inversely related to the resistance. That is, blood flow will be elevated by either an increase in pressure or the decrease in resistance. So another topic is about the control of the cardiovascular system. So the regulation of this process occurs primarily through cardiovascular neural control mechanisms that are integrated with sensory information received from the peripheral circulation. So in general, control of heart rate, arterial blood pressure, and the ventricular contractility arises from higher brain centers located in the cerebral cortex, referred to as central command. So in turn, central command maintains precise control of the cardiovascular system by directing to the cardiovascular control center. So there are four primary regions of medullary cardiovascular control center plays important roles in maintaining cardiovascular control. So number one is the pressor area. The pressor area, cardiac acceleration center, and the last one is the cardiac inhibitory center. Autonomic nervous system. So, in response to inputs from central command center, the periphery, the medulla sends neural output signals to the heart and blood vessels via the sympathetic and parasympathetic divisions of the autonomic nervous system. So, these autonomic nerve fibers travels to the heart and blood vessels where they exert control to heart rate and the blood pressure. So the difference between sympathetic control and parasympathetic control is the sympathetic control nerve impulses that arise from the sympathetic nervous system are transmitted by cardiac accelerator nerves or the sympathetic nerves to innervate the heart and blood vessels. While parasympathetic control naman niya is where nerve impulses that arise from the parasympathetic nervous system are transmitted by the vagus nerve to innervate the SA and the AV nodes and atrial ventricular myocardial cells. So, amo ni siya illustration nga kapakita nga effects of the sympathetic and parasympathetic nervous systems on the cardiovascular function. So the last one is the peripheral control. So the cardiovascular control centers receive sensory information from a variety of mechanical, chemical, and thermal receptors located in peripheral circulation. So these receptors operate by establishing a specific set point to help maintain cardiovascular homeostasis. For instance, the mechanical receptors or the mechanoreceptors sense changes in blood pressure, blood volume, and muscle tension, whereas chemical receptors or the chemoreceptors sense changes in blood gases or the oxygen and carbon dioxide. So that's it. Thank you for listening. Have a good day.